let's get started. So I'm trying to mix it up this year with this class, and that involves kind of switching the order of how I'm teaching some of these things, and in particular, I thought it would be useful at the outset to kind of give you a picture of what this field looks like today. I think, as I said at the end of last class, it has the connotation of being a really old, stale or dead kind of field, and it's quite the opposite. I mean, it's incredibly rich. It's one of the richest areas of research in what is termed soft matter physics. The history of it is immensely rich. The problem of trying to solve the shape of the elastica, which is the true shape of a bent beam. We're used to doing stuff like in mechanics of materials and even structural mechanics where we focus on small deformations, right? We say like, okay, let's assume the angles are small, let's assume the deformation is small, and let's solve for the deflection of our beam. But the question of like, what's the deflection of the beam when the deflection is really high dates back to the 1700s with the Bernoulli family, among others, working on this problem, Euler as well. And just trying to solve this launched areas of mathematics, launched the study of elliptic curves, elliptic integrals. And it kind of has this, I think, incredibly rich history to its name, but it's also kind of right now incredibly active. There are tons of people doing research in this. And that was the point of me asking you to read this review, partly to gain some intuition about structures, but then also to get a sense of what is being researched in this area. So I was hoping to try to break down this, I guess, digital wall, was to try to see if we could just start a discussion with either comments or questions, conceptual or technical, on some of the topics that were covered in there. I would imagine it was not super easy to read. I would imagine there are a lot of terms that didn't really make any sense, and this would be a good time to kind of maybe chat about those. And I'll explain, you know, if they matter or if they don't, or how they can help you going forward. So let's start. Let's. What do people think while reading this? Comments or questions, especially folks who are remote, feel free to like unmute yourself and shout something out. And, yeah.
I guess I'm just wondering, when it comes to negative Poisson ratios, how, other than the foams that you talked about, like how exactly is that achieved? Because it's still kind of.
Yeah, sure. So there's a question about, I don't know if the folks at home could hear, but it was a question about negative Poisson ratio. And this is one of those things that I feel like always generates a ton of interest. And just to remind you of what negative Poisson ratio is, let me switch to and draw something really quickly. So typical materials if you push on them, they kind of get squashed, and they will. Actually, let me do this a little bit. And they will. They'll do this. So under some load, a typical material will do this. And you'll notice that, just so that everyone's on the same page, what we've done is we've lowered the top of this thing by some amount delta. but then the width of this thing has increased by some amount. Actually, I'm going to switch these variables. We're going to call this one U, and this one V. And this is a typical material. You squish it, it widens out. Conversely, you take the same material and you stretch it. By some amount. And it shrinks there. The Poisson ratio is essentially the ratio of those two strains. So you have your Poisson ratio is going to be the negative of the, I always get this backwards, the axial over lateral, negative y over x. So we're going to do, I'm not going to write this in words, we're going to say it's the negative change in, let's see here, we'll call this the width W, oops, we'll stick with our normal variables, width B, length L, and so this would be kind of like your Poisson ratio is negative V over B over roughly U over L. And typical materials do exactly this. You push on them, they get fatter. You pull on them, they get skinnier. They get skinny. Usually it's in all three directions. And until about 20 years or so ago, this was kind of all we really talked about with materials. And then people started to realize that if you push on foams, you get a different behavior. Another material that's a little bit strange is cork. And cork is a material that has zero Poisson ratio. Push on it, doesn't get fatter or shrink in either direction. This is why cork makes a nice stopper. As it kind of expands or contracts in the vertical direction, it's not going to let air through on the sides. So it makes for a nice material for kind of plugging a liquid vessel. At the heart of the Poisson ratio, we just do it in this kind of macro scale deformation. If you were to go back to your Mechanics of Materials textbook, there is, in most Mechanics of Materials textbooks, a derivation of Poisson ratio from the geometry of like a crystalline lattice. And what you see is that it's really at this kind of micro scale that when you pull on this lattice this way, the lattice kind of contracts this way. It looks something like this. Like imagine you have a lattice that is like this. So these are chemical bonds, and the atoms are the blue. And as you pull this, it kind of does something like this. And so it's really geometric in nature. And so your question is kind of like, well, how else do you do it? A foam is one way. But the foam, what's happening is you're playing with that geometry. You're putting voids in there. And so you're altering the geometry on the small scale. Maybe not on the molecular scale, but you're altering it on like a micro meso scale, like something like not really big enough to see usually, but not small enough that it's microscopic. And what you're doing is you're adding in defects that are going to force it to kind of deform like here. You're basically changing the geometry that is, when you pull on it, now there's voids in certain spots, and so you see this behavior there. So in short, most of the ways in the last 20 years people have figured out how to make negative Poisson ratio materials are by playing with geometry, playing with the micro or mesostructure of the material. The reason why this has become incredibly interesting and popular is with 3D printing and laser cutting, it's really simple to put very precise patterns of either cuts or holes or printing things with voids in certain spots. And that's what you kind of saw in That's what you're seeing here. These things don't need to be super small. So the pink is what I'm looking at here. So these things don't need to be super small. Here's one where they're engineering in constraints to make it so that these holes can only deform certain ways, and they get a material that basically exhibits really no Poisson ratio here. Then they can change around the constraints on this geometry and force it to have either positive or negative Poisson ratio. So it's really geometric. It's really something that we think of as a material property. And for most materials it is, because if you go down to like the microscalar, you can kind of calculate what's happening in that material from the geometry of the molecular bonds. But you can play with it by changing geometry. And so there's a lot of ways you can do this, whether it's, in this case, putting in holes here, putting in slits in paper by cutting it. It's incredibly geometric. And so people have been engineering negative Poisson ratio structures by playing with geometry and not necessarily playing with geometry. Like foam is much smaller than these. These are literally like this big. Like these holes are probably, I don't know, the size of your fingernail. And the structure itself is probably, this big here. So you can engineer these things on the macro scale to get a bulk behavior that usually is something that's prescribed on the material scale. Does that help a little bit? Yeah. Cool. This is one where there's a ton of interest because I think Nike put like a negative Poisson ratio outer layer on a certain pair of running shoes to kind of like prevent it from stretching in areas when you would have impact loading. I don't know, it's hard to know sometimes. Like a lot of these companies are now looking at 3D printing either soles of shoes or the tops of shoes for performance factors. Because like the sole of your shoe, you usually want like the ball of your foot and the heel of your foot to be really like kind of stiff and absorb a ton of energy. So when they hit the ground, that energy is not going into your bones, it's going into the material of the shoe. But the spot in between the heel and the ball of your foot, you want to kind of be really flexible so you can kind of flex your foot as you're running. So there's a lot of like, people are trying to engineer these, material properties that are, we call them metamaterials because they don't occur commonly in nature. This is not like, it's very rare to find negative Poisson ratio material. So people are trying to engineer these things in. Yeah.
Following off of that, like you said, it was like you gave little. Has there ever been done like on a bigger scale?
Yeah. The cool, and this is why I think this is one of the things that people don't talk enough about with mechanics in general, structural mechanics, is that for the most part, these things are scalable either to massive scales or to incredibly small, but like just above like the molecular scales, like and like the microns to hundreds of nanometer scale. So the principles that we're using here, so for instance, to derive some of the equations or to predict with the deflection of something, will work, from massive scales to really small scales until you get to kind of the really quantum effects. One of the areas that these types of mechanical metamaterials are really being utilized on a larger scale is with deployable structures for aerospace things, especially the origami stuff, where like you're gonna send some sort of solar satellite or something out into space, and you want this thing to kind of open up and deploy in a particular way. And these types of structures can be scaled up to that size where we know what the mechanics are going to do. And so I think there was, I don't know if it's still there, I think there was an architect. That's the other thing. A lot of architects have been using some of these ideas for like building facades and for like deformable like shades on windows. And I think there's an architect at MIT that had put up a structure that was huge structure that exhibited a negative Poisson ratio, and it would kind of be deforming in the wind. can't remember exactly what it was. I'll try to find it and see if it's still there. But yeah, these things can scale. That's one of the benefits to learning the stuff that I feel like goes undersaid is that as long as you understand the relevant energies at play, you can scale them accordingly. What I mean by that is like, you know, at the beginning of the paper, we talk about the elastogravity length scale. So at what scale does gravity start to matter? So that's something you have to keep in mind if you're scaling it up. It's like, okay, is gravity going to start to deform this? Maybe I need to make it stiffer here or something. But these things can, in general, scale massively. So. All right, how about some folks online?
Professor, I had a question regarding the warping wafers. In the paper, it says that homogeneous heating of a bimetal plate will endow the plate with a homogeneous natural curvature.
Hold on, give me 1 second. I'm just trying to turn the volume up so we can hear you right. Hold on 1 second. Try again.
Okay, so I was asking a question about the warping wafer section. There was something here where it said that homogeneous heating of a bimetal plate will endow the plate with a homogeneous natural curvature. Does that mean that everything would have to heat up at the same rate? But if there's a curvature, would that then change? Like, I was just a little curious about that part, just because like I recently started baking and I started noticing the like how much the metal sheets like warp while they're in the heat, and then when I take them out, they like come back and like snap back.
Yeah, absolutely. That's a great question. So if your baking sheet was a flat piece of metal, you stuck it in your oven and had it kind of perfectly levitating in your oven and heating it uniformly all together, it'll just get bigger. It's going to uniformly get bigger in all directions. But if for some reason maybe your baking sheet is on a metal rack and the metal is hotter than the air, or maybe the baking sheet has a rim around the edge, so that rim is maybe restricting its ability to get bigger in one direction, then what can happen is you get what's called differential heating. So the most basic thing about differential heating is in what are called bimetallic strips. Are people familiar with the bimetallic strip? Take so you're familiar with from mechanics of materials, and I'm gonna come back to answering your question. I'm just gonna take a brief aside. So in bimetallic, you're familiar from mechanics of materials, I think, the idea that if you have a bar and you heat it up, then there'll be some strain, thermal strain, that's like thermal coefficient of expansion, so a material property that says as you heat it up, it's going to get a little bit bigger, or some strain per degree of temperature times the amount you've changed the temperature. Okay, so this is just basic mechanics of material. You heat something up, the material, you think about what's happening. What's temperature? You have two atoms next to each other. They're kind of vibrating at room temperature. You turn up the temperature, they start vibrating more wildly, and so then their distance gets a little bit further apart. You do that over 10 billion molecules in a material, and the whole thing gets a little bit bigger. So people realized really long ago that if you take two metals that are different and you glue them together, then you have a problem, because now the blue material might have a material property so when you heat it up it expands a ton, and the pink material might have a property where you heat it up and it expands a little bit. Just a material property. It depends a little bit on the arrangement of the atoms and how easy it is for them to get excited when you turn up the temperature. And so what happens? And what happens is, if the blue material needs to get a lot bigger, so we heat it up, the blue material wants to get like that, and the pink material wants to get only a little bit bigger. So the blue one, when you heat it up to a new temperature, it gets huge. The pink one, you heat it up, gets a little bit bigger. But remember, if these things are stuck together, there has to be some way for the blue one to get bigger while the pink one gets a little bit less bigger. And so what happens is the thing will bend. And so it won't stay flat. I'm not really drawing this to scale, but you get the idea. And this thing will bend. We call the curvature of an object in its stress-free state. Like when you have an object is just sitting there, we call that its natural curvature. And it's like 1 over. So this is a radius r. And that's 1 over that radius is its natural curvature. Before I get back to the wafer buckling question, this problem is another one of those massively historically significant problems, because people were trying for a long time in the 1700s, again, to make better and make it easier to navigate in long ocean travel. So you get a boat, you want to go from Europe to the Americas. How do you go and navigate properly to where you're going? And it turns out the key to being able to navigate properly before GPS, it was to be able to tell time incredibly, incredibly well. If you tell time, you can know where the sun is. You can know that every 4 minutes is one kind of degree of the Earth's rotation. And so if you can tell time incredibly well, you can know where you are based on where the sun's location. So the task of figuring out how to go on long Atlantic voyages was really in the hands of clockmakers. And one clockmaker. And so the challenge with keeping time really well is you're out on the sea, temperatures are fluctuating a ton, humidity is fluctuating a ton, there's salt in the air, the barometric pressure is changing a ton. So you need a clock that's going to keep time as all these properties are changing. And the temperature fluctuation was one of the biggest issues. And so this clockmaker figured out that you could make one of the components of the clock have a instead of being made out of a metal strip, it's made out of this bimetal strip so that it kind of adjusts itself naturally based on the temperature. It just kind of bends a little bit to account for changes in temperature. And he just knew from playing with the material how much it would bend depending on if it was this temperature or that temperature. And this led to a breakthrough in making better clocks, which meant better travel across the Atlantic. These things are still, well, I guess not really anymore. If any of you grew up in a house with those like circular dial thermostats that you can kind of turn to change the temperature, the way those things work is there's a coil of bimetallic material in there, and that it figures out what temperature it is by how curved that coil is. So this is how bimetals work, but this can also work the same if you have if you just have a single metal and you apply heat, you apply like more heat, and you apply more heat over on one end than the other. That means you're kind of heating up this end really fast. So this thing will still bend because the top of this metal is hot. Sorry, I guess the bottom, the way I drew it. Wow, that's huge. So the bottom of this metal would be hot, the top of it would be cooler, and so it'll bend to account for that. That's the differential heating. You've heated one side more than the other. So going back to the wafers problem, what's happening is that you have this material, probably it's not being heated uniformly. Most likely you put it on a metal rack in your oven. That metal rack in the oven is a little bit hotter than the air, so the bottom of the rack is hotter than the top. And so this whole thing is trying to warp. And the whole thing is trying to adopt a natural curvature that's exactly based on this bimetallic strip idea. And so it's trying to warp into a sphere. I think this is the point where I talk about here, yeah. The theorem of egregium. Did anyone have any, I'm sure this is not something that people have encountered before. Is that true? This is a long way of answering your question, but I will get there. This is my favorite theorem in math. And with what we learned yesterday, you can do a ton of like just intuitive structural mechanics work just by knowing these two things. So what we did last class is we compared bending energy to stretching energy, and we said as objects get thinner, it becomes incredibly easy to bend them and incredibly hard to stretch them. So for thin structures, stretching is really, really, really hard. What Gauss did was he found that you can if you look at an object, you can, for a beam, I already drew the natural curvature of this object. It's curved in one direction. It's a 1D thing. What's the curvature? It's what I drew here. So that's how it works for a beam. For a plate or a shell, there's obviously two directions. So if I were to take a sheet of paper, I could say, what's the curvature in this direction? So this we can call kappa 1. And I could also ask, what's the curvature in this other direction? Kappa 2. So curvatures are not a scalar. They're actually just like stress. They're typically represented as a tensor. So that means you would say that I'm going to have, my surface is going to have a curvature in the one direction, curvature in the two direction, and maybe there's some twisting. So there could be like a curvature in the 1, 2, and a curvature in the 2, 1. Typically, whenever we have a matrix, one of the things, well, you should do it if this has not been kind of beaten into your head yet, is can you diagonalize this thing and find the principal components? So get these two things in the off axis to be 0. You probably remember how to do this. If you don't, we'll do it in more detail later this semester, but don't worry about it for now. But there's a way to generally take any matrix and turn it into that, right? People with linear algebra, dusting off the cobwebs. Okay, so these are called your principal curvatures, and they're what I've drawn here. It's the curvature in the one direction and the curvature in the two direction. Let's go back to linear algebra. Does anyone remember the two eigenvalues of a 2D matrix? Nothing? No one? I got the determinant and
this is like great guess, but like AC minus BD.
yeah, so that's your determinant. Perfect. So AC minus BD is going to be kappa 1, kappa 2 minus 0 times 0. So it's going to be, in this case, when it's diagonal, it's just the product of the two there. So this is 1. I'm going to call it big K. Who remembers the other one? It's simpler than that one. That's the determinant. What's the simpler operation you can do on a matrix?
The identity matrix, maybe?
You're close. Yeah, that is That is an important one, but that's not what we're looking for here. So you took these two things and multiplied them by each other, and then subtracted off the half diagonal product. What else can you do to the? Then remember the trace being the other thing. The trace of the matrix is just adding up these two things. Is this ringing a bell? If it's not, it's okay. I mean, I thought it might, but. So usually you take a half of it. Well, I'm gonna do this a different way. No, you don't. Okay, I'll write it like this. So any 2D matrix, these two things are the two eigenvalues of it. Take the determinant, take the trace. These things in our warping wafers problem and the Gauss's theorem play a really, really important role. So this thing here is called your Gaussian curvature, named after our friend Gauss. Since this is the average, the bottom one is the average. You're just taking the two of them and dividing by 2. I just have the 2 on the other side. Then this is what's called the mean curvature. Okay, so back to Gauss. Well, so the Gaussian curvature of a piece of paper is really trivial. What is it? It's exactly equal to how curved is your flat piece of paper in this direction times how curved is your flat piece of paper in this direction? 0. It's not curved at all. So your Gaussian curvature of your flat piece of paper is exactly 0. Don't worry, I'm going to get back to the warping wafers, I promise. So K here is exactly 0. So now there's 2 other options. One is we could draw like a basketball. And again, we could say, well, I have a curvature here. I have a curvature here. So the Gaussian curvature of your basketball, we can't tell you exactly what the number is, but we can say that no matter what your choice, if you wanted to say that this is a negative curvature or this is a positive curvature, I'm pointing at K1 here. It doesn't matter if you take the product of 2 negative things or the product of 2 positive things, the Gaussian curvature of your basketball is always going to be positive. People see that? It's definitely curved in both directions, doubly curved. The third option is that there's a sign change. So you take your potato chip, Pringle, and you say, okay, I got or a saddle, if you're more of a horse fan. Kappa 1, Kappa 2. Now, no matter what you define to be positive, the other one's the opposite. So your Gaussian curvature of a saddle is 2. Is negative. Sorry, is negative. Okay, these are the 3 options. What Gauss said and proved is that it is impossible to change the Gaussian curvature of an object without stretching or tearing or putting holes in it. You probably know this. Like, have you ever tried to, I don't know, give your kid brother a basketball for Christmas and you decide, I'm gonna wrap it with wrapping paper. You can't possibly wrap a sphere with wrapping paper without crinkling that paper. It's mathematically impossible. So you can't switch. It's impossible to switch between any of these combinations without stretching. And we know that thin things don't like to stretch. So it's impossible to take my thin object and wrap it around a sphere perfectly or wrap it on a saddle without stretching, and this thing is not going to stretch. So the Gauss's Theorem of egregium that I read about there was basically just saying you can't go between here and here, or here and here, or here, any of these combos without stretching, and thin things don't like to stretch, so you're never going to do that. So how does this relate to the warping wafers problem? Well, when you're heating up a beam, you're asking it to go from flat to this curvature here. When you heat up a plate, what you're asking it to do is to go from a flat plate to be curved into this kappa n in this direction, and to be curved in kappa n in this direction. You're asked, when you differentially heat up that baking sheet, you're trying to get that baking sheet to curve into a sphere. It doesn't want to curve into a sphere. It's actually impossible for it to curve into a sphere. So what it does is it buckles. It finds a different way to deform. How does it do that, and what does it deform into? Well, what it does is, for thin sheets, it finds a deformation that costs no stretching energy at all. And when your baking pan in the oven buckles, what it does is it's trying to buckle into a sphere. It can't, and so then it warps into a cylinder. A cylinder is curved. And it's incredibly easy to take your sheet and wrap it into a cylinder. But if you notice this thing here, I have my cylinder here, it's curved in this direction. So kappa 1 is some number, but it's flat here. So kappa 2 is exactly 0. So your cylinder is a shape that has no Gaussian curvature, but does have a mean curvature. Because kappa 1 is some number and kappa 2 is 0, so then your mean curvature is just going to be the 1/2 of the kappa 1. So what happens to your baking sheet is it's differentially heated. It tries to warp into a sphere. That becomes so energetically costly that it buckles. And what does it buckle into? Well, it has to be curved because you're heating it up, so it's trying to curve. And so what it does is it says, I can't buckle into a sphere, I'm going to buckle into a cylinder. This here, and I'll pass this around. None of you at home can see this, maybe you can. So this is a plate that we made in my lab, and it's made of two materials. They're both made of rubber. The top layer is green, the bottom layer is pink. And what we do is we play with the chemistry so that when you glue these two things together, the pink material shrinks and loses material. It loses like a little bit of fluid, and the green material absorbs that fluid. So instead of heating it, instead of there being differential swelling where the green is getting warmer and the pink is getting colder, instead of there being differential heating where the green is getting hotter and the pink is getting colder, this is what's called differential swelling. It's almost like you had two sponges, one that's like really absorbs a lot of fluid and one that doesn't, and you glue them together. And basically water moves from one side to the other. This green layer gets bigger everywhere. It wants to be a huge big plate. The pink layer, which you can't really see, but I'll pass it around, gets smaller. It tries to warp into a spherical shell. Can't do it. Gauss says no. It buckles into a cylinder. So we can use this as a way to kind of create structures that change shape on command. If we use different stimuli, we can get them to switch back and forth between one and the other. So this is up to you. And so people are using this idea, which comes from some really fundamental mathematics of the properties of a surface, to design structures that will deform certain ways. So that's how your baking pan warping in the oven. It's trying to warp into it's trying to heat up into a sphere that's too energetically costly. So instead it buckles and adopts a cylinder shape which has no Gaussian curvature, so Gauss is happy, but it has a mean curvature, so it's bent, so it's still maintaining equilibrium. It's actually bending to account for that differential heating. Surfaces that can be deformed into each other without stretching they have a special term. I think it's in that paper. It's called developable. So for a flat sheet, there are essentially two. There's technically three, but the third one's a little bit confusing. There's technically two ways that you can develop the sheet. You can wrap it into a cylinder. Now it's got mean curvature, but no Gaussian curvature. Or you can wrap it into a cone. And everywhere in this cone, except for the very, very, very tip, which I don't actually even have on here. So if you actually had this cone have a solid tip there, that would be tricky. This is a developable shape, and you can see it. It's like anything you can do to bend your sheet without stretching it. Basically means anything you can do to your piece of paper that's not hard. You can kind of do this, kind of roll it around. And so in general, if you see, this became a huge problem when people were working on laminated composites. You take fiberglass and you put epoxy on it. I'm a surfer, so you make surfboards by taking foam, put fiberglass on it, put epoxy on it, and then you get a really rigid outer core. So if you take fiberglass, coat it with epoxy, throw it in the oven to make that epoxy turn into a hard solid, what would happen is, if you're not very careful with how you heat it, your composite laminate turns out just like your baking sheet, and it warps into these shapes here. And so engineers spent a lot of time in the 1980s figuring out proper ways to lay up composite laminates, so that way when you heated them to cure them, they wouldn't warp. This is still a problem. So I don't know if you know, but the BU Epic Lab has a variety of 3D printers, but they also have a metallic 3D printer. One of the main issues in making structures with these metallic 3D printers is that there's tons of residual thermal stress. You're putting this metal down at an incredibly high temperature, and it starts to warp the structure, just like you're seeing in your baking sheet or the material that I'm passing around. And so a lot of them trying to figure out how to better use metallic 3D printing is trying to figure out, how do we get this residual stress, this like stress that's stuck in there because of temperature, away from the part that we're trying to print, and we want it to be flat, or we want it to be this shape. So it's a big engineering challenge trying to mitigate these types of deformations that occur due to the way you heat a structure, or the way you swell or grow an object. This thing pops up all the time. And if you just remember, you can't switch Gaussian curvature without stretching, and you can't stretch thin sheets. Like, that tells you a lot about what you're going to see in the deformations of thin objects. So that's a great question. I hope that long-winded answer helped make some sense of that.
Yeah, thank you, Professor.
All right, what else we got?
I read there was something in the article called the Vlasov something. Hold on, let me try to find it.
Let's see.
The Vlasov operation.
Yeah. Is that in the SI?
SI?
Is that in the supplemental info, or is that in the main text?
Wait. Maybe I read a little bit. Yeah, I was in the SI.
Oh, yeah, okay.
I guess I read a little.
That's all right, yeah. That's way down here. That is here, that little like lozenge shaped operator?
Yeah.
Yeah. That is horrendous, isn't it?
Mm-hmm. Can you elaborate on that a little bit, please?
Sure. So this is, I would say, just for curiosity's sake, because you will never encounter this until you are far along in a graduate curriculum. But you're familiar with operations like the gradient, divergence, the Laplacian. The Laplacian is the divergence of the gradient. The thing to the left of this equation, so we'll start up here. I don't know if you can see that. You can't see that thing. So the thing that the upside down triangle next to the 19A, so it goes B, upside down triangle, the fourth W, that is what's called the Bi-Harmonic Operator. It looks awful, but it's really, the beam equation is just fourth derivative of deflection times B is equal to 0. That's your beam equation. And you solve this. You might not remember, but in mechanics materials, you definitely solve. You integrate 4 times, you apply 4 boundary conditions, and you find the equation of the bent beam. So that the fourth derivative is how that looks in 1D. In 2D, you need to account for derivatives in X and derivatives in Y. You still have 4 derivatives, and so you end up with this Bi-Harmonic operator, which is basically saying d to the 4th w dx to the 4th plus d to the 4th w dy to the 4th plus the mixed terms of x and dy. This other awful operator comes about from looking at, so you're probably familiar, maybe not, you might be familiar with the Jacobian. You have a matrix of like first derivatives, and looking at the properties of the matrix of first derivatives. So you can look at stuff like how much the Jacobian will tell you kind of like, if you deform something, how much did the volume increase, or how much did it get sheared? Just like you can construct a matrix of first derivatives, you can construct a matrix of second derivatives, which typically relate to curvatures. Typically relate to slopes. Second derivatives typically relate to curvatures. This equation looks horrendous. However, it's basically just, if you have a matrix of second derivatives, which is what's called a Hessian, then you can calculate kind of the Hessian between 2 matrices of second derivatives. You get like, look, it sort of looks like a determinant, right? It's like thing top 1 times bottom 1 plus, it's almost like almost analogous to something like a determinant for a matrix of second derivatives. And so a lot of what you're seeing, to get back to the bigger question, is like the equations of mechanics, solid mechanics, fluid mechanics, dynamical systems, are really complicated. There's often 3 or 6 or 9 of these equations that are really similar, but like you have to keep track of all the different dx, dy, dx, dc. So what people do is they try to make their notation more compact by saying, I keep seeing this one term. It looks like what I have next to that number 16 right up here. And I'm just going to collect all that thing into one operator and say, if you give me anything for f and g, I can spit out something at the end that'll basically tell you how 2 quantities are coupled together. Like if you put in the displacements, you end up with something that is a exact way to calculate the Gaussian curvature. That's a little bit more mathematically like detailed than the way I drew it up here with like the spheres and the saddles and stuff. So think of it as just like an operator. You feed in G and you feed in F, and it spits out a thing that is based on how the second derivatives of those quantities change. But I wouldn't worry about it unless you're really like PDEs and stuff. So. All right, other questions?
It's just a random question.
Yeah,
like,
yeah.
What's your favorite, like, I mean, I guess I won't say topic, but like, what's your favorite part of what you do?
So the thing I've spent a long time working on these structures. So this C and D are mine. Actually, I think I actually might even have one here. Like, these are all ways that we play with trying to generate different shapes by, I'll pass these around too, by playing with, already passed up. So I spent a long time working on these things. And it kind of, I was going to answer it a different way. I probably will show you both, but I love this because it's so fundamental and it just keeps showing up in different ways. So all we're doing is playing with taking a material and asking it to locally either stretch or shrink and say, what shape are you going to find? So the things we're passing around, this thing is, the pink is going to shrink, the green is going to stretch. This is kind of like, it would never make this shape if you did this, but it would make a saddle shape if you did this. And that is, if you could imagine having a bicycle wheel and tightening the spokes too much, you'll eventually buckle that bicycle wheel. And that bicycle wheel will stop being a nice circle and it'll kind of warp in some way. It's trying to warp, not necessarily like this, but like this here. So I'm bringing this up not because this is my favorite thing at the moment, just to say, as we keep studying this, we keep finding examples of when differential swelling of a thin object turns out to be really, really important. I'll give you one example, which we haven't published yet, so this is kind of stuff that we're still working on. But right now we're studying how the human eye forms. And so what happens is you end up like the human eye kind of forms, you have this like forebrain. This is gonna be my like total physicist mechanics version of development. You have this kind of forebrain that spits out these little things. Who knows what's over here? So again, this is not biology. This is mechanics stuff. And basically what you find is that if you zoom in here, and you look at it under a microscope, this looks a, oops. That's a terrible drawing. If you zoom in, that kind of looks a lot like a spherical shell. So that is where this is what's called the optic vesicle. Vesicle is like a stack, like a fluid-filled stack that has a little bit of, it's really soft. And it looks like a spherical shell. And what happens is, as your brain, your body develops, this thing starts to turn itself inside out, like this. And then in that little shape there, that's where your eyeball sits. It sits like in a little cup called the optic cup. And so just by playing with those shapes that I was showing you in the review paper, and just by understanding like, okay, if you grow here and you shrink here, what shapes will you make? We developed a model for the morphogenesis of this optic cup to say, okay, here are all these parameters that biologists have measured. We think this is the problem, just like the pink and green things in that review paper, where we say some parts are growing fast, some parts are growing slowly. If we just think that this is a spherical object where some parts are growing, so for instance, if this is a spherical object where this part is growing really fast and this part is growing really slow, and you give it no biology, you don't give it any biological clue. You just say, what if we just pretend that this is just a sac, a spherical sac, where the pink part's growing fast, the orange part's growing slow? What shapes will you see? And it turns out, using all the parameters you can measure in biology, what you get is that this is exactly the same as a little snap through instability, where this thing essentially is growing, it turns itself inside out, and it forms a nice little cup for this eyeball to sit in. And we can say that if one of the cool things we found is that if the properties of this thing here are a little bit different, like if it's a little bit thin or a little bit too soft, then it won't form the right shape for an eyeball to go into. It'll form, your eyes will develop abnormally. And so just by studying how thin shapes work when they grow, we're starting to understand the growth of really basic physiological things without the physiology. We're basically saying, actually, the way your optic cup forms that your eyeball sits in is mechanical. It's a structure. It's a spherical shell that's growing fast in some parts and slow in others, and we can model that shell the same way we'd model it from the stuff in this class, and we could tell you, hey, this is the way your eyeball is developing. So this has been really exciting. Although the thing I think will be more cool, and the thing I'm probably most excited about at the moment, is we've been doing a lot of work on what's called Kirigami. This is in the thing as well, right? Kirigami is basically like take a sheet, put cuts in it, and pull on it and see what it does. I think that's down. Do I have a figure in Kirigami? Oh yeah, up here. Okay, cool. So the top row here, stretching. So that's Kirigami. You put cuts in a sheet and you pull on it. We've found that you can make really cool structures by putting cuts in these sheets. And the thing that we found, I'll show you a video. So just by playing with where you put the cuts and the shape of the sheet, we have recently see if I can find this. Sorry, give me 1 second. Oh, that's terrible quality. Hold on. You can kind of see it. This is the sheet we made in our lab. It's attached to a robot. All it is a sheet of plastic, mylar. Doesn't really matter what the material is. We put cuts in it in a certain way, and we warp it into a cylinder. And then if you pull on it, it makes a really great gripper. It can pick up a ton of things. It's picking up a M&M, picking up a raspberry without squishing it. You can take these objects and you can put them together in series. guess the video kind of gives, the picture gives it away. And you can use it to pick up tricky objects like a pencil. Or you can put these objects in series and parallel. And you can pick up and rotate 40. These are like incredibly slippery, like little hydrogel beads. So just by playing with where you put cuts in your sheet, you can make really functional structures. Like we've made this robotic gripper. We have made these linear actuators. So here's an object that when you pull on it, you can get all the components of this thing to rotate. So these little plates here are kind of rotating as you pull on it. You can generate both lift and pitch. So this thing is going to be started out perfectly flat, and then we pull on it and it pops out. Actually, I think it's that's the first tilt, and then it pops out, so you can generate lift from your object just by putting cuts in it. This is just a sheet of like plastic. Like literally, you could do this with paper, but you probably would like have to be careful where you put the cuts because it might tear. But if you pick a material that's a little bit hard to tear, you put cuts in the right places, and you can make all these functional structures. Here's my favorite, where we get this thing to kind of roll. So we're pulling on it vertically, we're pulling on it up and down. And those sheets just spin around the axis there. I will point out that all these blue things you're seeing here were done in my lab by an undergrad who was just playing, really. And we basically said, can we make something that can spin? And he just spent a ton of time with the laser cutter trying different combinations till we figured out how to make something spin. And then we figured out why it worked. And then now we kind of design something like that. But this is all research that was done here by undergrads who were interested in structural mechanics. So I think these are probably the things I'm most excited about at the moment. These Kirigami structures, because I feel like there's an endless combination of things that we can do, and it's just a matter of kind of understanding a new way of thinking about structures, like putting cuts in, seeding defects, putting holes where you want them to get the type of behavior that you would want to design in there. And what's cool about them, I think you were the one that asked this question earlier, is like, how does this scale? What's cool about the things I just showed you is we worked with some folks who do things on graphene. You know what graphene is, y'all? Like it's the thinnest material in the world. It's a monolayer of carbon atoms. So it's the thinnest possible material in the world. It's got all these crazy problems. So it's as thin as a material you can possibly get. So we did some simulations simulating graphene, where we put our cuts in the graphene sheet the same way we put them in the sheets in our lab. And the mechanics that says if you pull on this thing with these cuts here, it'll do this on the macro scale. We predict the exact same thing on the scale of graphene, thinnest material in the world. So we can, like, these ideas that are just from structural mechanics translate from stuff that you can hold in your hand to stuff that you can do on the thinnest material in the world. So I don't know, that's kind of probably where I'm most excited about at the moment. I think there's a ton of ultralight, creative, deformable, shape-shifting structures you can make by just playing with like cuts and folds and stuff like that. All right, give me some, what else we got? Give me some other questions. So the eggshell thing was super interesting. This is exactly related to the Gaussian curvature. The stiffness of your object increases with the Gaussian curvature of that object.
I think that's off like the pizza.
Yeah, the pizza. So this is a really cool thing about that. So if you take a sheet of paper that you have in front of you and hang it off your desk, you'll notice that it'll sag a lot. I don't know if the folks at home can see that. Yeah, you can. It sags a ton. If you just simply like curve it like a cylinder, I'm just going to take the ends of my sheet and warp it up just a little bit, tiny, tiny bit. This thing is remarkably stiff now. It doesn't sag. If I put my fingers down, it drops. This is Gauss's theorem of Residual. This is the exact same thing. Why? Well, this thing is flat. It wants to bend. It's incredibly cheap to bend this way. However, if I add a little bit of curvature to it, now think about what has to happen. For this thing to bend down, it has to bend. I don't have enough hands. Let's see. It has to bend. There we go. It's already bent like this, but now it has to bend like this too. So now it has to have two curvatures, a curvature in this way and a curvature in this way. Now you're asking it to bend like in this case, a saddle, right? And we know that it's not going to do that because that would require it to stretch. It doesn't want to stretch. We can't change Gaussian curvature. So it remains, it basically is a way of stiffening this material just by adding a tiny bit of curvature, which is what you do when you eat pizza. If you have a floppy piece of pizza, you kind of fold it and you eat it like a folded in half piece of pizza. Why? Because when it's folded, it's too hard for it to bend down like this because it would have to stretch and it's not going to do that. What's cool about this is that people have recently, this is an article published in Science. A friend of mine who's a remarkable shell theorist, Marcelo Diaz, was working on the theory behind this. But what they showed is that there's a lot of evidence that bipedal locomotion, the fact that we can walk on 2 feet, has to do with the fact that the bottoms of our feet are doubly curved. They're curved. You have an arch to your foot that runs from like your heel to the ball of your foot, but there's also a slight curvature in the other direction. The great apes and other species like similar enough to us to compare to have a flat foot in the direction from like big toe to small toe. So they'll still have the arch in this way, but they'll have it be flat in the other way. And the contention is going back through the historical fossil record and seeing the evolution of that arch, that doubly curved arch in your foot, is what enabled the humans and Neanderthals and other species of humanoids to be able to walk on 2 feet because of the extra stiffness that their foot has because of that double curvature, which is super cool. I think. Like, I mean, the connection of some of these very structural things to human evolution of walking or the development morphogenesis of the eye. Like, I think it kind of speaks to how so much of these things really relates to the structure and the mechanics of them. I thought the wrinkling would gather more attention. Did anyone actually try to wrinkle their skin and see if they could see the wrinkle patterns form? You just kind of pinch your forefinger and your thumb together, you see kind of an undulation there. This is a really simple model. It's just using the same bending energy that we've learned, right? And all it does is, this equation number 10 here should look familiar to you. It's sort of like the energy of a spring, like kx squared, but we replaced x with delta. And now we have this integral, which is probably a little bit like, all right, where'd that integral come from? kx squared is the energy stored in one spring. What people said is imagine your skin is like a stiff layer sitting on an infinite number of tiny springs. So like imagine your skin is here and you have a bunch of tiny springs here. Now we know that we're going to try to, if we were to smush this object, so I'm going to take it, I'm going to push. The blue thing wants to do this. The thin film, like the thick outer layer of your skin, wants to do this, right? That's what happens when you push on a bar. It buckles into mode 1, right? You probably remembered that when you did the buckling analysis or the buckling in mechanics of materials, there was like a equation that had a mode number in there. We said, no, it's always 1, and so we just put in 1 for that. But you could kind of force it into mode 2, or maybe even sort of mode 3. So this blue thing wants to do this. But now think about the springs. That would make these springs over here stretch a ton. That's a massive amount of stretching there. So there's a cost. The bending wants to bend into an arch. The stretching wants it to basically stretch as little as possible for each string. So if the if the stretching was in control, it would want it to do this, where each spring went up like a little bit. But now you're asking this blue thing to bend a ton, right? The curvature of this thing is super small. The radius curvature is super small. The curvature is super large. That's a lot of bending energy. So what happens is your wrinkles adopt some sort of balance in between the two. It says, all right, I want to bend into this big arch. You want me to bend into this tiny thing. Let's meet somewhere in the middle, and we'll find a wavelength that's kind of like somewhere in between those two things. And so what dictates that wavelength is a balance of how hard it is to bend the object relative to how hard it is to stretch the springs. And then based on just dimensional analysis, in order to get a length scale here, there's a fourth root on that. And dimensional analysis just meaning the same stuff you learned in fluids. Like, how do the units work out? We know lambda is a length. Lambda is a length. How do we get a length from just comparing these two things? People have been using this to create surfaces with wrinkles that control adhesion, to create surfaces with wrinkles that can make a compound eye. They made what looks like a fly's eye, where it's like a spherical shell with tiny little spherical shells all over it. They made like actual lenses. These things appear a ton in morphogenesis, development of thin structures, again, actually near the eye. Another professor, Professor Jason Bird's research group, just had a really beautiful paper on the cover of Science, talking about wrinkling that can appear in fluids, like fluid bubbles. Really, really viscous bubbles will actually wrinkle, and they'll have wrinkles that kind of are, as they start to pop, or as that bubble starts to drain, and behaves a little bit different, but there's a really nice kind of connection between fluids and solids there. So I thought that would be kind of cool to talk about. I think of anything else. I think one of the biggest takeaways I would want you to have as structural engineers is, for the vast majority of the history of solid mechanics and structural mechanics, one of the main goals of a structural engineer was to prevent instabilities from happening. Like, I'm going to design a thing that I don't want it to buckle. Makes sense. You know, if you're designing a column that's holding the beams in this room up, you don't want that column to buckle under a load and this whole thing collapses. But over the last like 20 years, there's been a shift, as one of my colleagues says, from buckleophobia to buckleophilia, of like, how do we embrace the fact that these things can go through instabilities, and can we use those instabilities to make functional structures? Can we make things that can switch really quickly between two shapes? Can we make something that can exhibit a behavior that you can't see in a normal structure by taking advantage of these instabilities, patterning structures, and so on and so forth. Yeah. Did anyone have any trouble following through on the derivations of the elastogravity and the elastocapillary length scales? Are there any questions there? They're kind of important, and I want you to know them. The elastocapillary one probably doesn't feel as important, but this is the reason why those of you still with a full head of hair, well, your hair clumps together when you get out of the shower. It's because your hair is thin rods. Fluid, it wants to wet that material. And as it wets it, it kind of applies a little force to it and starts to tug on it. And if that structure is bendy, then those things will coalesce. You dip your paintbrush in paint, and all the bristles come together. They're not separate anymore. This became really important for people who are making, if you want to make stuff on a really small scale, like lithography, for making computer chips, something, you kind of take a wafer, put a material on it, put a mask on it, shine light. Wherever the light touches, it makes that liquid film solid. Then you dip it in solvent, and you're left with whatever you made solid standing there. And that's how people make all the computer components. But people are also trying to make, like, for a long time, there was this effort to try to copy the fingers of a gecko. You zoom in on the fingers of a gecko. So geckos obviously climb walls, and some can climb ceilings. They're really, really incredible adhesive objects. And if you zoom in on their fingers, there are these millions of tiny pillars that are really long and skinny. And if you zoom in on those pillars, on top of the pillars, there's another set of really tiny pillars on top of each individual pillar. And the idea is that that kind of gives them the ability to kind of conform to whatever surface they stick their hands on, and then they can kind of peel off and climb. And due to, I don't know if you remember van der Waals attractions from chemistry, due to van der Waals attractions, these things are really sticky. They adhere. And so for a while, people were trying to make these tiny pillars using photolithographic techniques. But what they kept finding was happening, I don't think I have a picture of it. What they kept finding was happening was that as you dip them in the solvent, all the pillars would just collapse together, like your hair in the shower with a paintbrush. And they're limited by this length scale here. They can only make them this tall before the fluid starts to pull them all together, coalesce, and then you can't make a tiny pillar anymore. So now people have used alternative ways to try to make better adhesives. But yeah.
Are they still working on that, or is it big difference?
Yeah, so people have found that. So I think as a result of people basically banging their heads against the wall on how to make those adhesives, what they found was actually what you really want is something that coat, so they want your adhesive to really perfectly coat the material it's coming into contact with, and also be really soft once it's coated in. They call it compliant. It's soft. And so people basically said, well, shoot, we can't make these solid pillars. Can we make this thing compliant other way? And there's this product that is, I think, just coming to market now. It's called Skin. You should, like, there's cool videos of people using Skin. It's this remarkable switchable adhesive. So Skin, Gecko Skin. It's this remarkable adhesive. My favorite video, to be full disclosure, did my PhD with the person who invented this thing. I started working on it just before I graduated, but they did all the cool stuff. I just kind of saw what they were working on. And there's this awesome video of them walking around with like a big screen TV, something that's like bigger than this thing here. And they had a slab of this Skin on the back of it. And it's just these two graduate students just like wandering the halls of their college and just being like, all right, I'm gonna stick it to this wood. And they just leave this thing there. And they go pick it up and then they go and wander to like bricks and they stick it on the bricks and it sticks on the bricks and they peel the TV off and they go and move it on like glass. And it's just remarkable. It's on YouTube. It's remarkable to see this reversible adhesive that is entirely based on a balance between getting the film to touch every part of the wall, but then also be soft once it does, compliant once it does. And they make it so that it's incredibly strong and shear, but incredibly soft and peel. So it doesn't want to slide down, but if you try to peel it, it's really easy to peel. It's really cool. You should definitely check out the videos of Skin. I remember like he brought some home and his kid accidentally threw it in like the washing machine and like it took it out and then it still worked perfectly fine afterwards. And I think of like trying to do that with a piece of Scotch tape, like your Scotch tape is not coming back from that. So it's really cool. So people have absolutely been working on ways to kind of mimic gecko adhesion, but I don't know that anyone's figured out a way to form those structures that you see on a gecko. I think it's incredibly hard, like, to engineer that type of thing. Any other questions from the audience? From the Zoom folks? This is mainly what I had for you all today. I wanted to kind of introduce you to what I think of as modern structural mechanics, like what's going on in this area right now, to kind of show you that a couple of things. One is this is a really active area. If you find this stuff interesting, it's not just designing trusses for bridges. There's a ton of really cool avenues going in, from just studying fundamental like morphogenesis in biological systems to designing better adhesives to designing structures that can morph and change shape on command to designing better soft robotic tendrils, things that can act kind of like our fingers do. This is a really rich area, and what's cool about that is, and it's going to be really hard to keep up the momentum on this, because in order to learn this stuff, there's a lot of like, okay, we've got to write down, here's a beam, and it's going to be loaded here. How do we calculate the deflection of it? I want to keep in your head that the math you're doing and the ideas you're working through scale and they translate. And so even if we're working on some cartoon schematic of like a beam that's being loaded here and pushed on here, these ideas translate to tons of different areas. If you can understand the mechanics, you can often either identify like, oh, that's buckling because of that, or or we need to add some more of a stiffener over here because this thing's going to fail right there. These concepts are, in my opinion, like incredibly fundamental to the development of mechanical engineers. And then beyond that, as we're seeing, and I hope you saw in reading this, are applicable in a huge array of problems. And so being able to do structural mechanics and to think about how structures deform will be vital to kind of applying these concepts to kind of any area that you end up working in that involves any sort of an object or structure. And I don't think our textbooks do this justice. I don't think the way we often teach it does it justice. And so I wanted this to be a way to show you all kind of the richness of this area, because I do think it's an incredibly rich topic. I didn't give you a break today, so why don't we just end early instead? If you have any other questions, feel free to shoot me an email, anything, curiosities, or otherwise, and I'm happy to keep chatting about it. And then we'll pick up doing some more structural mechanics on Thursday. All right. Thanks, everyone.